One other type of reaction rates are called relative rates, and this is using the balance equation and the coefficients and essentially looking at the mole ratio. So this is your stoichiometric relationship. So we're using mole ratios from our balance equation. That means we're using coefficients. So I'm going to jump right into an example because I think it's better understood through an example than rather me trying to give you the definition to begin with. So let's take a look at this reaction. We're producing oxygen gas and nitrogen monoxide, and it says the initial rate of formation means to make or made, is 0.60 molar per second. So at a rate of 0.60 molar every second, nitrogen monoxide is made. So just look at your balanced equation. It should really tell you something. Since the coefficient of NO is 2 and the coefficient of oxygen is a 1, then I know something about their relative rates. Since the coefficient of NO is twice the coefficient of oxygen, then I can suspect that nitrogen monoxide is made at a rate twice that of oxygen. It's going to be made twice as fast, and that's exactly what happens because its coefficient is double. If I look at the coefficient of your reactant, NO2, it's a 2. So the rate of NO is equal to the rate of NO2 because they have the same coefficient, a 1-to-1 ratio. So however fast NO2 is being used, that's the same speed at which NO is being made. That is relative rates. That is that stoichiometric relationship. That is using the mole ratio. But we have this very technical way of writing relative rates of change. So in part A, they want us to write the relative rates of change using a particular format. Since rate is change in concentration over change in time, I need to write down delta concentration of NO2, the reactant. So we're measuring how much the concentration of NO2 is changing divided by the change in time. That's the initial rate for NO2. But since it is a reactant, we're going to put a negative sign in front because its concentration is decreasing. And then we're going to put a fraction in front. It's going to be 1 divided by 2 because the coefficient of NO2 is 2. So we're going to make the denominator the same as the coefficient. We're going to set that equal to the rate and change of the oxygen gas. So we do the same thing, delta O2, delta T. But this time we're going to put a plus sign in front because oxygen is a product. We are making oxygen, or the reaction is making oxygen. But again, we're going to multiply by a fraction. 1 over 1, because the coefficient of oxygen is a 1, it gets a denominator of 1. Repeat for your last product, concentration of NO over concentration, or change in time. A plus sign because it is a product. And then the fraction is going to be 1 over 2 because the coefficient of NO is 2, so the denominator is 2. What this is essentially saying is that if I examine O2 and put everything with respect of O2, O2 is being made at a rate that is half the rate of NO. Oxygen is being made at a rate half that of NO, and that's because its coefficient is 1 and NO's coefficient is 2, so 1 is 1/2 of 2. And then I can say, okay, well, O2 is being made at a rate that is also half the rate at which NO2 is being used. And that, again, goes from the coefficient. Coefficient of oxygen is only 1, but the coefficient of NO2 is 2. Okay, so how do we summarize this into some usable format? As you can tell, we write change in concentration over change in time. That is rate. Okay, so we're going to use this change in concentration over change in time. That is the format. But then we have to remember that reactants are disappearing, so they get a negative sign. And products are being made, so they get a positive sign. You don't have to put the plus sign, but I did for emphasis here for you to recognize that it is a positive change in rate. And then finally, that fraction in the front. The fraction will be 1 over the coefficient from the balance equation. Okay. That's relative rates. That's how we write relative rates. We put a fraction in front, which is essentially 1 over your coefficient, and then the formula for rate, change in concentration over the change in time. So part B is asking us, what is the initial rate of formation of oxygen gas? Well, they told me the formation rate of NO is 0.60 molar per second. This is stoic. Okay? So if NO is being made at a rate of 0.60 molarity per second, that's for NO. Multiply that by the mole ratio. 1 mole of O2 for every 2 moles of NO. So essentially what we're doing is you're dividing it by 2. So half of 0.60 is 0.30 molar per second. Okay, and that's exactly what I would think would happen, is because I look at the balance equation, the coefficient of oxygen is a 1, and that of NO is 2, so I would suspect that oxygen is only going to be half the value of NO, which is exactly what we have here. Part C, what is the initial rate of disappearance for NO2? Given that the rate of formation for NO is 0.60. Again, multiply by mole ratio. 2 moles of NO2 for every 2 moles of NO. So we're going to get 0.60 molar per second.